In this video clip, let's talk about logical data, which is true or false. In the past, before C99, which is the standard set forth in 1999, C programmers used other data types, such as integer, okay, before C99. They use integer to represent logical data. What does that mean? Well, if you look at this entire integer plane, this goes into the negative, this is positive, and there's 0 in the middle. So what happens is if you use the integer to represent logical data, false is always 0, okay? But everything else is true, right? Including a value that's negative 23, for example, and true could be 1 million. It doesn't matter. As long as the number is not 0, everything else is true. This is still true in C++, by the way. But that said, effective C99 standard, that standard introduced the Boolean data type, and that is true or false. So now that we have true or false. So in the following slides, let's talk about these logical data, and also what we call truth table. This is in your logic in mathematics. It's the same thing. You know, when we have true, right? And right, true, this evaluates to true, right? Or something to that effect. We'll go through that truth table later on. Then let's talk about operators and also various different expressions involving these logical operators. And then let's go through the comparative operators as well. So this will be the basis of today's this video lecture. So this is our logical operators truth table. If you look at this, so AND is represented by double ampersand in C, C++, in Java, and Python. And when you have a double pipe here, this is what we call OR. Okay, so you probably studied this as well in math. When you have AND, right, the truth table says, and of course, you know, these would be the operand, right? Operand. So operands could simply be an expression itself, right? So as you know, expression evaluates to a value. So on both sides of this ampersand, which is the what we call operator, right? So similarly, the double pipe OR is an operator as well. So this is a Boolean expression. So when you have operands on both sides and it's using an AND, this is the truth table, right? So if X is false, right, and you try to do AMP, right, to another false right here, right, the end result is false, right? So on and so forth, false, true, true, false. So with respect to this operator AND, A-N-D, if any one of the operands is false or is true, it still gives you a true, right? So in order for this entire expression, this binary expression, true to be true, you'll have to make sure that both operands are true. Okay, so that's AND. And or if one of them turn out to be true, then the end result is true. Okay, so this is very different from OR. There's also the complementary, right? So the complementary of the other. So if X is an expression that evaluates to true, right? The complementary of that is not true, which is true. However, if X is true, then not, right? X, right? Then it would be false. So these are the standard logical operators that we see in C, C++, Java, and some of the contemporary languages today. So how does your computer evaluate these Boolean expressions? So when you have false, false, right? And true, right? Or anything, right? So there are two ways to evaluate it, right? So if you're somebody who writes this program, you would think computer has to evaluate this and then evaluate this and then, right? N, right? This thing to evaluate the entirety of the expressions. Similarly for OR, right? And this is N. You would think that you would want to evaluate this, right? Thinking on behalf of your program, and then the program have to evaluate this, right? To arrive at the end result. But if you study the truth table, you know that if, let's say, one of the operators in an AND, right? situation is false, then you know this is false already. Similarly, if you have an or expression and one of the operand gives you expression gives you true, then you know the result is true, right? So there's really no need to have to evaluate this at all, right? So do you think your C program is going to have to evaluate this anything here at all? It turns out the answer is no. This is what we call short circuit method for and or. So in fact, your C program is pretty smart, and this is true in C++ as well. Your computer, as soon as your program evaluates, right, having this in place, having this display, if evaluates, if one of them is false, immediately this will be short circuited. So this part is not going to be evaluated, not evaled, okay? Similarly, if you have an or, if one of them is already true, especially the very first one, and this is not going to be evaled because you already know what the end result is. So your C program would immediately go for this path without having to evaluate it. So this is what I meant by short circuiting methods. In fact, this is true in most of the languages out there. All right, let's go through what we call relational operators. So there's several of them. In your mathematics, we come across less than, right? Less than or equal to, right? There's a greater than, equal to. In English, we don't ever say this is equal or less than, right? Or equal or greater. We always say less than or equal to, greater than equal to, right? So if you go by this order and simply expressing this order in terms of the operator, then that's less than equal to, greater than equal to, less than or greater than, right? So this is how we do things. We don't ever write, for example, this as this, okay? So we don't write this. This one cannot be written as this, okay? We don't write this in C or C++. Do not worry about the precedence. Actually, this is there's a ranking system. You don't have to commit the entire ranking system to your memory, but just know that the relational operator and how operators are composed in your program. Okay, so there's also equality. So this is comparing something, right? So when you have equals sign, you're comparing this something against this something. So this something is operand, right? This something is also another operand. So just remember, operand itself is an expression. It could be a single value, right? So it could be 1, right? It could be a, right? Characters. But anyway, and the complementary of equal is not equal. So not equal is using this exclamation point, okay? And you cannot write this as this, okay? There's no such thing. So always remember, not equal carries an exclamation point in front of the equal sign. So that's the equality. Let's move on to see a couple of examples. So this is the complement of the other. So what is the complement of less than? It's greater than or equal to, right? What about the complement of equal? Well, not equal, right? What about the complement of greater than? The complement of greater than is less than or equal to, right? So you got to cover the other thing. So if you look at the entire hemisphere of the problem space, if this portion is less than, then this other portion is greater than or equal to, right? Or in mathematics, that's how we express it. In C++, we use greater than or equal to that way. Same thing with, right? If some of the areas, so part of the problem space is equal to, and that will leave anything that's outside of the problem space be not equal to, right? So similarly, so just remember these things. Lots of times when you do control positive, and let's say if you want to turn the entire logic the other way around, you can apply the complement rule. Again, this is something that you might have studied in your logic class in either grade school or middle school. Let's look at this table here. This is actually illustrates a very important fact in programming. And in fact, it's true in math and sciences as well. If you have an expression that is as complicated as what you see here on the left side, right? Why is it complicated? Well, it is complicated because it's not easy to understand. If you think about a developer writing this code, this X and Y could be representing something else. And then you just keep on thinking, if this is greater than that, but you haven't negated the entire thing, right? So this is not exactly very simple, right? In fact, this is complex, okay, complicated. not easy, right, to understand. So what we do is we try to simplify what we can. How can you simplify your original expression into something simpler? Simply take the complement, right, of what this is. So if you were to negate the entire thing, you got to remember not only the entire, this has to be negated, it has to be negated, but most importantly, this entire, the complement, right, involving the operator has to be negated. So just remember when you have something like this, right, you try to negate the entire thing, right? So what is x less than y, right? The entire thing's opposite, right? Or the complement. It's what we call before, right? Greater than or equal to. So if this is x greater than y, then the complement of that is that, right? So this is the best, right, approach moving forward. So just bear in mind when you come across something complicated, there is always a way to simplify it. And in fact, you should always strive for simplifying these comparative operators. This is what we call comparative, right, operators. This is a quick illustration of various comparative operators. So we have a less than b, right? These a's or b's. That's usually integers here, right? None of this is a Boolean. So as you can see here, your format specifier represents digits. That's exactly what you need for these. However, when it gets to the relational operators, right? So this comparative operator, remember this evaluates to an integer, right? Namely Boolean. Right, so Boolean is an integer, zeros and right minus, plus 1, 4. Right, we talked about that. This is the reason why you're using digit as well, right? So that said, once you put them into this comparative operators, this entire expression, you get some digits out of it. Is a equals to b, right? Of course, the answer is no. So you get some results out. If it's a, right, less than or equal to, right, not or, less than or greater than, right, or simply not equal to b, and things like that. And then you can flip. In fact, you should practice this by writing this code, not copying the entire thing, but writing it from scratch to see for yourself. As you can see the results on the next page. This would help you understand how comparative operators, relational operators work in C and also C++.